Hey everyone! Today, we're tackling a concept that trips up a lot of computer science students in their theory of computation courses: ambiguity in context-free grammars. If you've ever stared at a parse tree wondering is there another way to do this? Then this video is for you. In just about few minutes, we're going to demystify ambiguity, show you how to spot it, and understand why it's such a big deal for programming languages. Before we dive into ambiguity, let's do a super quick refresh on what a context-free grammar, or CFG, actually is. Remember, CFG is a formal system used to describe a language, essentially, the set of all valid strings in that language. It's defined by four tuples. Variables, V, these are non-terminal symbols, like A, B, Q1, Q2. They represent transition states. Terminals, sigma, these are the actual characters or tokens that appear in the strings of the language. Production rules, V, these are the heart of the grammar, showing how variables can be replaced by other variables and terminals. For example, SA/A. Start symbol, S, one special variable that kicks off the entire derivation process. Alright, with that in mind, let's define ambiguity. A context-free grammar is considered ambiguous if there exists at least one string in the language that can be generated in more than one distinct way. What does more than one distinct way mean in practice? It boils down to two key indicators, which are essentially two sides of the same coin. Before we dive into ambiguity, let's do a super quick refresh on what a context-free grammar, or CFG, actually is. Remember, CFG is a formal system used to describe a language, essentially, the set of all valid strings in that language. It's defined by four things. The parse tree method is often the most intuitive visual way to spot it. Think of it like a road map. If there are two entirely different valid paths on the map to get from point A to point B, that part of the map is ambiguous about the best or intended route. Incorrect program behavior. Your code might do something completely different from what you intended. Compiler errors or warnings. The compiler might just give up, or warn you about the ambiguity. Inconsistent results. The same code could behave differently on different compilers or even different versions of the same compiler. Essentially, ambiguity breaks the fundamental principle that a program should have one clear, unambiguous meaning. Let's illustrate this with the most common and clear example, a grammar for simple arithmetic expressions. $e\right arrow e plus e\mid I dot d dot dollar. Here, E stands for expression, and ID stands for an identifier, like a variable name X or Y. We use these rules to derive strings, and a common way to visualize this derivation is with a parse tree or derivation tree. Each internal node is a variable, and its children show the production rule applied. Now, let's try to parse the string, ID plus ID. Parse tree 1, multiplication first, correct precedence. Host. In this first interpretation, we apply the rules in a way that respects standard mathematical operator precedence, multiplication before addition. $e\right arrow e plus e dollar. Our main operation is addition. Now we look at the right $e dollar. We want to do multiplication here. So $e\right arrow e dollar, fill in the IDs. $e\right arrow I dot d dot dollar. $e\right arrow I dot d dot dollar. $e\right arrow I dot d dot dollar. We start with $e dollar. This derivation naturally groups the ID together first. So, it's interpreted as ID plus ID. This is usually what we expect. But what if we applied the rules differently? We start with $e dollar. This time, let's first go $e\right arrow e dollar. Thinking the multiplication might be the outer operation, now, the leftmost $e dollar needs to become ID plus ID. So, $e\right arrow e plus e dollar. Then we fill in the IDs, $e\right arrow I dot d dot dollar, $e\right arrow I dot d dot dollar, $e\right arrow I dot d dot dollar. This second parse tree groups the ID plus ID together first, interpreting the string as ID plus ID. This completely changes the meaning and violates standard operator precedence. Because we found one string, ID plus ID, that can be represented by two structurally distinct parse trees using this grammar is unequivocally ambiguous. If this were a grammar for a programming language, it would cause chaos. So, what's the solution? We need to rewrite the grammar to remove the ambiguity. This usually involves introducing new non-terminal symbols and structuring the rules to enforce operator precedence and associativity. For our expression example, we'd introduce rules like $e ri e plus t mid Taiwan dollar ri tf mid f dollar, and $f ri id mid e dollar, which forces multiplication to be handled before addition. We'll save the details of how to rewrite for another. The key takeaway for you right now is this: an ambiguous CFG allows a single string to have multiple meanings or structures. Your job, when analyzing a CFG, is to find if there's even one string that results in two or more distinct parse trees. If you find one, the grammar is ambiguous. Hopefully, this has cleared up some of the confusion around ambiguity in CFGs. If you found this helpful, hit that like button, subscribe for more CS content, and let me know in the comments if you want to see a video on how to resolve ambiguity. Thanks for watching, and I'll see you next time.